Chapter 9, Part 2, Attenuation and Gain. Attenuation is where a signal loses its amplitude over distance. In other words, the voltage is decreasing over time. Frequency, it's important to note, will not be decreasing. Basically, this is just a gain that's less than 1. And we know the voltage gain is the voltage V out over V in. Power gain is a very similar equation. It's just power out over power in. So if we were told the input power is 2 watts and the output power is 10 watts, obviously the multiplier is 5, the gain must be 5. 10 over 2 is 5. If, on the other hand, the input power was 3 watts and the output power was 9 milliwatts, watch out for the units here. This is a lot smaller as a number because of the units. So we do output divided by input and we get 0.03. This is less than 1, so this is an attenuation. So that's what attenuation is. It's just a gain that's less than 1. Our exam board does like to write it in terms of decibels, and there is good reasons why people like to write it in terms of decibels. Before we delve into decibels, we do need to understand logarithms because they work logarithmically. So I've got a set of equations that we all know. You may well tune through this bit if you do A-level maths. So 10 cubed is 1,000. In log form, I could say that this is log base 10 of 1,000 is 3. Similarly on the next one, I could say that log base 10, so this is the base, remember, of 10 is 1. On this next one, we've got log base 10 of 0.1 is -1. So it's telling us the powers. Now we'll only for A-level electronics look at log base 10. Obviously there are lots of other bases. We do look at log base E in timing circuits, but we're given all the equations, so we don't really need to understand how to rearrange them. Similarly, you should be able to arrange from log into normal form. So both of these will be useful. So this is saying that log base 10 of 100 is 2. So 10, in other words, 10 squared is 100. This is saying, remember this is 10. If it's not written, we're assuming 10. 10 to the 4 is 10,000. And this last one is saying that 10 to the 0 is 1. Now notice that the power is basically telling us how many noughts we've got. And if it's negative, it's telling us how many places below the decimal it's got. So that's logs. It's telling us all about powers. And it's kind of easier to see logs because these numbers are quite small. 3, 1, -1. They're very easy to kind of comprehend, whereas obviously 0.1 and 1,000 is very difficult to kind of scale those two. So humans like logs, and we like to work in logs, which brings us to decibels. Decibels work in terms of logs. And you can, so what we do is we take our gain, power out over the power in, and we then take the log of that number and we times it by 10. Now, this starts with Alexander Graham Bell. A normal bell would actually be 100 log base 10 of power out over power in. We look at decibels because they're the lowest volumes we can hear. So 1 decibel is about the lowest we can hear. Okay. You do so notice that this number, ignore the 10 because that's just the multiplier at the front. Ignore the 0. This is just telling us how many zeros we've got. So 2, we've got 2 zeros. It's 100 times. The gain is 100 times the input. And we've got 1 0. And notice when it goes negative, that tells us that we've actually got a loss, an attenuation. So this tells us it's 1 place below the decimal. This place is -2, ignore the 0, 2 places below the 0. So it's much easier to kind of see what's going on, what kind of multiplier we've got. You do need to be able to rearrange this equation. So you would divide by 10 and then take it out of log form. I'll do that in a minute with some actual numbers. It's a bit easy to do with numbers. Let's look at some examples. And we're going to look at 4 examples. I would recommend you pause the video now and have a go at these 3 yourself first, and then I'll go through them. The 4th one is particularly difficult, so I wouldn't recommend you try that on your own. Okay, so first example, signal input has input power of 3 watts and output power of 9 milliwatts, exactly like we just looked at. So you stick it in your equation. So the output power is 9 milliwatts and the input power is 3 watts. Watch out for your units, of course. And you stick that into your calculator and you get that the gain is minus 15.23 decibels. Don't forget your units because we're measuring decibels. Okay, that was quite simple. This one's a bit more difficult because we do have to rearrange the equation. So again, we've got the same formula. We've got the gain this time of positive 17. So we know that it's a multiplier. The output is bigger than the input. And we're putting it into the formula. And we know that the output power is 2 milliwatts. And we don't know the input power. So we're going to have to work that out. Divide by 10. Now we need to take it out of log form. This is where you need to be comfortable getting out of log form, which is tricky. So this is telling us 10 to the power of 1.7, which is a horrible number. I don't want to know what it is. I'm just going to leave it as 10 to the power of 1.7 is 2 milliwatts divided by the input power. I now rearrange. I multiply by the power in and divide by 10 to the power of 1.7. So the input power is 2 milliwatts divided by 10 to the power of 1.7. So divided by a number that's a little bit less than 100, but a lot more than 10. And I would put that in a calculator. And I get that the input power is 0.0399 milliwatts. In other words, it's really, really small. But we expect that because the output power should be a lot bigger. So our 2 milliwatts should be a lot bigger because we've got actually 17 decibels. That's almost 100 times bigger because 20 decibels would be 100 times bigger. Remember that this is effectively a normal gain of 100. So that's the gain in decibels, and that's the normal gain as a ratio. And 10 decibels would be a gain of 10. So 17 is almost 100 times bigger, which is what we'd expect. So it's just a little bit less than 100 times bigger. You could convert it into microwatts if you wanted. Okay, question 3. We get given a bit more information here, and we got to worry about kilometers. But again, first things first, stick it in the equation, work out what the gain in decibels is. So we've got 10 log 10. The output power is 11 milliwatts. This is attenuation. This is a loss over 515 milliwatts. So the gain in decibels is minus 16.9897. Not a very nice number, decibels. I'm asked to calculate the power loss per kilometer. So this is the overall loss, 16.9897 decibels. And we want it per kilometer, and it's 9 kilometers, so we divide by 9. We're assuming it's fairly uniform. Or in other words, it loses the same amount of power every kilometer. So this would be our answer divided by 9. So that's minus 1.89 decibels per kilometer. We're asked to write it as a power loss, So we get rid of the negative because that just tells us it's a loss. So the gain in decibels, the loss in decibels per kilometre, we just get rid of the negative sign, 1.89 decibels per kilometre. Okay, last question. This is definitely the most tricky. So we're given the input power, we're given the output power, and there's a few different gains going on here. So firstly, we've got our equation, and we know that the overall gain in decibels is 10 log 10 input over output. Sorry, output over input. So 5 over 10, both in milliwatts. Milliwatts will of course cancel in this case. So that is minus 3.01 decibels. Now, the nice thing about this is we know that normally gains multiply. So if I have one amplifier that has a gain of 25 and I go to another amplifier that has a gain of 10, then the overall gain will just be 25 times 10, 250. However, when we're talking in decibels, it's kind of easier. So we can see this if we think back to that table. Each of these, we don't need to multiply. In fact, we can just add them. So when you are talking in decibels, this is an important thing to remember. For gain, you just add the values. So for gains in decibels, add them. So important thing to remember. This is the addition rule of logarithms for those students who do A-level maths. We just need to remember to add them. So we've got a 10 decibel gain here, and we've got 14 kilometers, and we're losing 2 decibels every kilometer. So the overall loss, 14 times 2 is 28 decibels. That's a loss, so that's a negative. And we know that overall it's negative 3.01. So this gain, so this is a positive plus this positive, minus 28 is minus 3.01. So we've got 10 minus 28, because that's the loss in the middle of the cable, plus some unknown, let's just call it x, is equal to minus 3.01. So x is just going to be equal to 10 minus 28 minus 18. So x minus 18 is minus 3.01. So x is 11.01 decibels. Not 11, sorry. $14.99. Sorry, I couldn't add up there for a second. So 14.99, basically 15 decibels. Okay, that's it. Do go through this last one particularly carefully, and this idea that when gains are in decibels, you add them. When gains are in our standard way, you multiply. So when gains are in decibels, remember to add them. And that's it for attenuation and decibels and gain and all this stuff. This will come up quite a lot in communications, so do make sure you're quite confident with it.